I was going to start the episode with a time travel joke, but nobody liked it. Science tells us that every action has a cause and an effect, but could something happen before whatever caused it? This is the core concept behind retrocausality, the notion that a cause might come after an effect. And while this is an idea most common in sci-fi, we have some indications it can happen, at least at the quantum level, which seems to leave the door open to it potentially occurring at a wider scale of space and time. We recently looked at a parallel notion, a causal events, in our episode Rocco's Basilisk, events that don't require time travel but have causes that almost seem to imply it, though it's a different scenario than retrocausality. Amusingly, that episode is actually a sequel to today's episode, which is also not the result of time travel hijinks. This episode originally aired on Nebula last year, and like a lot of our Nebula originals, I'm tweaking a bit before airing it on YouTube a year later, so you might notice my speech impediment is a bit stronger after this intro, being about a year of speech therapy behind. As with all our episodes, closed captions are available. I want to emphasize from the outset that this is not an episode that's going to answer all your questions about retrocausality. Some later did get written about in our earlier episode on Rocco's Basilisk. Past and present tense get very confused in time travel context, but we cannot cover all the scenarios, not just from time constraints, but because many are rather contradictory, and I feel talking about them at the same time would simply make them more confusing, which was part of why I had skipped Rocco's Basilisk in the original episode too. It's not the same concept at all, and constantly gets confusing for folks because they think there's time travel involved in it, whereas our topic today is very much about time travel and quantum. But even here, there's so many differing notions of how time travel paradoxes might play out that they can mash together into an incomprehensible mess, and retrocausality is confusing enough without including several different theories about the flow of time, alternate timelines, multiverses, or inconsistent timelines collapsing, which we have also discussed in our Time Travel and Time Wars episodes if you're interested. Rather, our goal today is to give some background on the retrocausality problem both scientifically and historically so you can think on it yourself, as we do not have an answer yet. Though the consensus for a lot of reasons is that retrocausality should be impossible, and we're going to poke at some of the suggested loopholes and mostly show why they are at best iffy in their functionality. We will be aiming for clear explanations or examples of how quantum allows time travel but that this does not scale up, which people say a lot but rarely clarify I've noticed, and the same for why wormholes can cause problems. So this is an overview of the science and philosophy underlying arguments about it we often see in sci-fi, not a formal presentation on why it does or does not work, and one will cram me into a shorter episode than normal, so I might jump around a bit, apologies in advance. You can do that in a time travel episode, and we'll still be at it for a while, so a drink and a snack is still advised. The idea of retrocausality is not just from quantum mechanics and sci-fi though, it is also popular in philosophical discussion of what cause and effect really are, which dates back at least to Aristotle's time, and they determined that any effect preceding its cause had to be an inherent contradiction, a belief that went mostly unchallenged till the last few centuries and remains a strong favorite even today. We also get four fundamental types of cause from this earlier speculation, which I'll cover quickly, along with a retrocausal example to illustrate the concept. Those four causes are the material, the formal, the efficient, and the final, and Aristotle reasons these are the types of answers we give to the question of why something happened, so it can include the metaphysical too. He used a table as an example. It is an effect, and our final end purpose is that we want that table to fit a goal, such as eating on it. That's why it was commissioned, and in a retrocausal sense, that commission might have been done to give Abraham Lincoln a splinter in his finger while eating, so he went to get that removed, and skipped on a visit to Ford Theater that fateful night he was assassinated. The efficient cause, or agent, is given to us as a carpenter who actually crafted the table, the agency that made it happen, and Aristotle offers us a parent as the efficient cause of a child, and we see this in retrocausality with the grandfather paradox, which has you going back in time to kill your own grandfather and in the process preventing your own birth. You removed that efficient cause, but could just have easily achieved that effect by delaying him at work one evening. This works fine in many alternate timeline scenarios, but arguably isn't retrocausal as your cause is coming out of another timeline. In a singular timeline, this would be an aborted process. You can't be born to prevent your own birth, but you might be able to cause it, which we'll get back to in a moment. We have the option of thinking of a timeline for someone as a long thread. Threads and weaving are popular in discussion of time travel and fate, possibly from the 3 Greek fates: Clotho, the spinner of fates and threads; Lachesis, the apportioner thread; and Atropos, which means inflexible or unchanging, sharing that root word of change with entropy. We normally picture time as running in a straight line, but if we're thinking of it as a timeline, a chord stretched between a beginning and an end, it is perfectly fine to have that include a loop at some point where it goes backward as it loops back, and this is the concept behind the closed time-like curve, or just a closed time loop. An individual's chord might be 70 years long, but only go between the year 2000 and 2060, as the person might have stepped into a time machine in 2033 and returned to 2023 to repeat that decade. And I'll explain how we do this with a wormhole in a minute, but it would normally require the time machine to have been invented by 2023, the earliest year you traveled back to, not the year 2033, the year you actually traveled from. This makes it hard to kill your grandfather unless he had invented that time machine. Thus it does offer us predestined loop events, like him not being your real grandpa but rather you all. You killed him by accident and comforted his grieving widow, or she got a crush on you. As I've mentioned in previous episodes on time travel, which I'll need to get around to writing one of these days, a disproportionately large number of time travel discussions seem to involve murdering your grandpa, sleeping with your grandma, or assassinating Hitler, or preventing the assassinations of Lincoln or JFK. In fiction, this is mostly just a plot device to do a period drama for an episode. They generally tend to ignore the butterfly effect aspect, which is basically knowing that very tiny changes inevitably result in big avalanching ones over time, and this would fall under the material cause or the formal, which can be a bit hard to define, but those two cover all more physical causes of a change, the blade of the carpenter's knife altering the wood, or the decay of time or the melting of ice over it to soak the wood and damage it. There's no deep insight here beyond recognizing that even a table with just one different atom, or it just being 1 nanometer different in location, or 1 nanokelvin different in temperature, are all alterations that can beget other ones. Even adding a single grain of sand to Earth's mass alters its net gravity, moving particles to different spots just a bit. Even 1 photon leaving an object to go through a portal to the future for us to observe the past has now failed to hit another object back then. Or 1 leaves your observer's lab, and that photon from your time strikes something, warming it just a little, or providing a tiny bit of photosynthesis. And this tends to result in people suggesting time or events have inertia or some inevitability to them to get around the butterfly effect and its temporal hurricanes, but this is a hand wave. Yes, it is very likely that if you distracted the first proto-human to play with a proto-axe, or that first artificial fire, that someone down the road would invent that axe or fire. But that is not an inevitability of time. That's a near inevitability of something specific, a thinking mind coming up with a concept and trying it out. If Einstein died, someone else would have worked out relativity down the road, if civilization didn't collapse in the meantime. But none of the present would look identical. Your parents aren't at the house they currently live in for you to visit them in an alternate reality, and you weren't born the same day and probably have a different name and look different too. There's no me telling you this in another reality because Isaac Albert Arthur didn't have parents name him after Einstein. Maybe I'm Isaac Feynman Arthur instead and focus more on quantum than cosmology. But the universe is different at every level because there is such a huge interconnection of events, even mundane, and they only pile up with time, they don't flatten out. But if your grandpa had died early, it isn't just you who is gone, it's me and everyone else watching this. We don't escape huge change even if Grandpa was a hermit with little obvious impact on others. And this handwave can slip in amongst the confusion as probable because it's playing with those other 2 more meta types of cause, the carpenter making a table on commission from the person wanting to dine on it, as opposed to which atom of iron in a knife sliced which molecule of wood in the lumber at which time and place. No intelligent agency is causing that wood to grow or decay either, but those are effect with a cause. Hence, we don't have to assume intelligent agency must be the immediate cause of a natural event. Incidentally, I'm introducing this Aristotelian notion of cause types because I've tended to notice people looking at time paradoxes will lock into some loop on one specific cause type, like Bob keeps going back in time to fix his problems and keeps returning to the same moment with each iteration of himself, while ignoring that Bob is changed. Bob is not the same collection of particles and states at each iteration of this event. Even the air he is breathing is not interchangeable, because some of those oxygen molecules are oxygen isotopes that decay and whose radiation might alter you where a different oxygen molecule wouldn't have, or would in a different way. Same for the carbon-14 you're exhaling, so it isn't actually repeating eternally, and once we abandon thinking of Bob as the same critter, we realize each of his interactions as a collection of slightly different particles is altering that timeline, be it the arrangement of the atoms allowing his memory, or the very slight different place he put his foot this time while walking somewhere, having cascading events that will eventually derail this repetition. So too, the person who keeps trying to fix past events, but always different ones, might be seen as stitching time. They keep making loops but to different places and each a new timeline, like a long line of stitches on fabric. If they're not new timelines, they are erasing their motivation to act. If they are, it doesn't actually matter how many changes they make to various different timelines or multiverses. There's no paradox. You didn't kill your grandfather, just a close copy in a different place. But we always come back to issues with retrocausality and the event eliminating the cause in the future. It only actually works in quantum because this is a different layer of reality where time, space, and matter are all emergent qualities. Think of a timeline you're drawing on paper. You can loop it however you please because those rules do not apply to you, and the macroscopic laws of physics are an emergent quality of the quantum scale. You could think of this as a higher layer of reality if you want, which is amusing since it's physically lower in terms of scale, but the key notion is it is foundational. Much as the laws of chemistry are to biology, even if a botanist in the 1500s might not know any chemistry, as biology is foundational to psychology, and yet a deep knowledge of chemistry or biology isn't a prerequisite there either, and that foundational aspect of quantum to our macroscopic world is that time doesn't flow forward or backward in quantum, or at least it doesn't seem to require it to do so for it to work. One popular notion was that if an electron moved back in time, it would have a positive charge. For the quick concept there, another electron near it that was anti on it should be repelled, normally, by its like charge, meaning it pushes away from it and the next moment is further away. Well, if that electron runs backward in time, that push happened a moment before, which means the other electron got shoved away from our time-traveling electron a moment before, which means outside observers would see it move closer as time moved forward for them normally. It appears attracted, as we would expect for a positively charged version of an electron, namely its antiparticle, the positron. Incidentally, by this reasoning, a mass moving backward in time should push things away from it as though it had negative gravity, or was a negative mass particle, and non-coincidentally this is why very nearly every time travel or FTL system requires negative matter to exist. We do not have any negative matter, and quantum gravity is problematic, but that's the origin point for why it is. Back to our time-traveling electron, which as we said appears identical to a positron, its antiparticle, and you probably are familiar with the idea of particle pair production and annihilation. I tend to discuss it in passing episodes on antimatter, and our upcoming one on vacuum or zero-point energy dips into it too. But we hold that, for whatever reason, tiny particles are constantly popping in and out of the void of space, and doing so in pairs that are opposite, and thus annihilate with each other a moment after formation. Another way of looking at it is that in reality there's an uncertainty to any bit of space-time, and we choose to view this as a series of temporary particle pairs, virtual particles, as this uncertain energy or momentum can have real effects around it and must be considered, and doing it as a particle is easier. One of the other ways of looking at this is that it isn't a pair, it's a particle moving forward in time, then moving right back in time, in a quick loop, so that it appears two particles ramming into each other annihilate. Folks often wonder why those two end up hitting each other, and the answer is they don't necessarily every time, but this perspective makes why seem more logical in my opinion. As usual with quantum interpretations, we have no known way of determining which version is right. They all correctly calculate the results we see, and so this idea that a particle erupts from nothing forward in time and then gets yanked back is as valid as others, and there are many of them, including Wheeler's suggestion that all electrons we see are the same single electron, and that all types of fundamental particles really only represent one single particle, just one electron, just one up or down quark, in the whole of space-time, and that's why they are all apparently identical to their siblings. It's kind of weird that all electrons should have exactly the same mass and charge, after all, planets and stars don't. But for our electron-positron pair, where we assume the electron pops in and moves forward then back to the moment of its creation, you might wonder why we can shrug and say that's fine, but that doing it with something larger is not. And that goes back to the uncertainty principle, the one that says that once we measure accurately down to the very small scale to a minimum of uncertainty, the more precise we know the position, the less precise we know the momentum, and vice versa. It's also true of the pair of quantities of energy and time, and our whole rationale for why a particle can appear from nothing for an instant this way is because its total energy is permitted to last for a tiny instant of uncertainty, more energy, tinier maximum moment of existence. The joke goes they're only allowed to exist for a moment before the divine auditor catches the error on the books, and the bigger the error or the longer it persists, the sooner it gets caught. Planck's constant is the maximum allowed error, and if you divide it by a particle's mass energy, you'll get that maximum time, and it's already tiny for an electron. In SI units, they've got a mass energy of just under 10 to the negative 13 joules, and Planck's constant is on the order of negative 34, meaning our temporary electron is only lasting on an order of negative 34 minus negative 13, or 10 to the negative 21 seconds, a trillionth of a nanosecond. For a proton or neutron at a couple thousand times that mass, they could exist for as much as 1,000th that time, a trillionth of a second. Given that the particle moving near light speed can cover a nanometer in a billionth of a nanosecond, and that's the scale atoms are at, and the same for atomic nuclei for the scale of those larger and shorter-lived particles, these temporary particles really do play huge roles in events down at that scale. These uncertainties matter and are the core reality, not a side note interrupting normal function. Not in ours, though. You or I have somewhere around 100,000 trillion protons, neutrons, and electrons in ourselves, and a particle or object of our scale popping into existence only would last something like 10 to the negative 53 seconds, which is so small it's a billion times smaller than even a Planck time, which we generally hold to be the tiniest unit of time that could mean anything. Nothing could even interact with you over so brief a moment, and the sudden appearance of a photon of your mass energy would have such a tiny wavelength and duration it might as well not exist, and indeed would be so compact it would actually be a black hole. Anyway, if we are using that forward electron reverse positron example of pair production and annihilation, you can have retrocausal effect from that positron running into another real particle, since that electron is running backward in time. We do actually use all these virtual particles inside our models for how atoms and atomic nuclei all work, so we assume if the particles can interact, which is required to be true for quantum to even work, then they can have their reverse time version interact and thus be retrocausal. You can debate if virtual particles themselves are anything more than a made-up physical object to ease calculation and conceptualization, but you get the same effect in other types of quantum interpretations. There's other examples in other models and approaches. This is the easiest one to explain though. You can probably see how this doesn't actually help with time travel too. Again, there are other examples in quantum, some operating on different issues, and we have similar cheats for entropy and Maxwell's demon for instance, but it tends to boil back to the same issue of it not being able to be scaled up beyond the level of Planck's constant, that minimum uncertainty or error or the universe equivalent of a pixel. What's allowed in that pixel doesn't translate to the bigger TV screen and the images on it. I should note that this still can't hit what we think of as the macroscopic scale. For instance, tiny though an electron is, it still has almost 1,000,000 times the energy of the typical photon you or I see, which in turn are millions of times more energetic than microwaves. A pair-produced photon of this sort can last for exactly one wavelength or frequency. Non-coincidentally, since photon wavelength and frequency multiply together to be Planck's constant, but they are photons with wavelengths the size of people, microwaves are an example, or even planets, or presumably galaxies or Hubble volumes, and so there are photons with frequencies longer than the blink of an eye, or the age of the universe. That's an interesting topic for another time though. Let's close with closed-loop wormholes, and I'll start by noting this sort of wormhole only can exist if you already have negative matter, or if you have matter running backward in time, so the entire example basically is stipulating that you can do time travel if you already have time-traveling things. The idea here is that time runs slower when you move faster, and so we make a wormhole and pin one gate to our laboratory and shoot the other out at 86% of light speed, the speed at which time runs at half its normal speed, then a clock attached to either wormhole mouth will show our lab version running at normal time and the other wormhole at half time. And this is just fine. If you jumped in the lab 10 years after the experiment started, you would pop out of that wormhole and see only 5 years pass there at that end. But it would take your signal back home longer than 5 years to get home, 8.6 more years in this case, and so you can't be sending on the lottery numbers. Nothing retrocausal has happened yet. But if I then bring my wormhole mouth back to the lab, taking another 10 years at 86% light speed, it arrives with its own clock only experiencing 10 years, while the lab has 20 pass. So if I leap in one side, I pop out 10 years earlier, but this is closed and can't permit time travel to before my wormhole existed. For me, this is all fine, since until someone shows me a negative matter particle, I view it as exactly as real and possible as a time machine someone wrote in a book. It works just fine, if we assume things that are not true. And it would seem to work just fine for fiction, but this is where the Aristotelian case type comes back into play, because we're treating this like two magic stargates with some person going through. In reality, a wormhole has way more complicated topology, along with insane amounts of mass and energy. And each of those particles has its own path, which tend to intersect with themselves when calculated. And recall a moment ago, when we were talking about what happens if an electron is going back in time, it becomes a positron. Likewise, a proton in you would now be an antiproton. Remember, you're just running backwards in time. You still pass through space doing this. It's not a hyperspace corridor or something. And I think everyone here knows what happens when antimatter and matter collide. And your path through that wormhole tends to involve self-intersection. Self-annihilation is certainly common in time travel math and mechanics, and often metaphorically in fiction on it. And we do have a number of theories from Hawking or Nokia or others on how alternate timelines that are not consistent must cease to exist, or how any successful backward jump must set off a sequence of events to disrupt its own cause from occurring and thus annihilate itself, but you can see our other time travel episodes for more on those. In the meantime, I suggest you grab a drink and a snack so you can have them for watching this episode. I mentioned self-annihilation a moment ago, and time travel is very likely to result in just that. Indeed, it is entirely possible that a successful time travel device might not just kill the user, but retroactively obliterate the entire civilization. But Doomsday does not have to be a downer, and if you're looking for a fun way for you and your friends to enjoy the end, let me suggest Doomlings, a wonderful new card game for the end of the world. Somewhere on a doomed and distant planet, life has emerged, competing for dominance until the world's inevitable destruction. Score points by playing traits for your Doomling species, making them more adaptable, resilient, and mischievous as the new ages occur and various creative catastrophes befall. I loved the game, and my kids took to it instantly with its amusing text, wonderful art, and easy-to-learn rules. Doomlings is a lighthearted, cheeky, goofy, funny card game that is easy to learn, quick to play, and still focuses on strategy. Find out more at Doomlings.com and use the code ISAAC20 to get 20% off your copy of Doomlings and enjoy the apocalypse. So we're done for today, but not the month, and we'll finish August up by journeying to the Gardens of the Moon to explore a period of early lunar settlement. Then we'll jump into September for more Space Fleet discussion as we look at stellar nomads, civilizations that roam the stars in immense armadas. Then we'll travel to the Library of Babel, a repository of all books ever to be written, and contemplate truly huge numbers while we're at it. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like Jupiter Brains and Megaminds at go.nebula.tv/isaacarthur. As always, thanks for watching, and have a great week.